Good afternoon, everyone. How are you doing? Fine. I think some of you are in exams, like I spoke with a few people. Is it all right? Okay. Are there any questions before we start?
Oh, I think I know the answer already, but from the homework, an enumerator that is ordered but can repeat means that it could, for example, do like 1, 1, 1, 1, 1, and then 2.
Yeah.
So it can repeat, but because it's ordered, it can only repeat the one that it's on.
That's what it means. Yes,
okay.
Exactly.
Okay.
Good. Last time we finished, in the last hours, we viewed some extra motivation to define an intrinsic notion of information in bit strings. So for fixed bit strings. And that is the program of algorithmic complexity. That's the idea of algorithmic complexity. We have a fixed bit strings, and we don't want to understand that it comes from a given set or that it comes from a given probability distribution. We don't mind. We just want to say, oh, is this random? That was one of the words I used, or not random? Or, in other words, can this string actually carry information content, or is it somehow empty? Like if it only has zeros, it seems like it's empty of information. Whereas if it has 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, one could say, oh, it might be encoding, some precious information coming from a hard disk or a book. So that was a generic idea. Now, enough for motivations. Now we're going to start with the real deal, the definitions. And let me call this section plain complexity. Okay, I'll briefly explain what I mean by plain complexity. In fact, we want to do algorithmic complexity. I will be using the word algorithmic complexity to refer to this concept. In the literature, it's also very well known as Kolmogorov complexity. It also has the name program size complexity or algorithmic entropy. It has various names. I'm going to stick to algorithmic complexity. I think if we can choose, my opinion on it, it's obviously only an opinion, is that if there's a name that is not the name of a person and that conveys a bit an idea behind, I think it's preferable. If I tell you Kolmogorov, you go, yeah, that gives me the name of one of the inventors, but it doesn't really tell me what it is about. Algorithmic tells you a bit more what it is about. Now I'm already commenting on the name, we haven't seen what it is, but even speaking of names and even before going into definitions, I just want to say that in fact there's two key notions. Algorithmic complexity comes in two key flavors. Some other ones that are derivatives, but two main flavors. One is plain complexity. And we denote it C. And the other one is going to be prefix complexity. Which we will denote K. Usually, algorithmic complexity has the symbol K, so I reserve the symbol K for the later version that we will see of prefix complexity. Now, just to give you a bit of an overview, the plain complexity is the one that has been discovered first. The original notion, I will say. Original notion. In the mid-60s. Okay, it was discovered by Solomonov, Kolmogorov, and Chaitin. What else can we say about plane complexity? It's funny, I'm telling you stuff about plane complexity without having it defined, but I think it works well. You get an idea of the names first. Yes, maybe a case can be made that is at least initially more intuitive. I'll say at first, it is more intuitive. More than this one. At first, less intuitive. And however, once we'll get there, we'll see that the plane complexity faces some problems which inhibits the development of the theory. Like, it's not that nothing can be said in the context of plane complexity. In fact, plenty can be said in the context of plane complexity. But at some point, we will hit some problems which we're like, oh, that's annoying. How can we solve those problems to have a richer theory? And this will be our motivation for prefix complexity. So I'll just say problematic for the development of the theory. Okay, that's my two notions. I've got plane complexity, prefix complexity. And now just to parallel what I have wrote here and what I have written here, during 10 years, plane complexity was the thing, was the algorithmic complexity. And it's in the mid-70s that Levin and Chaitin figured out how to solve those problems. So, yeah, this is the version of the, I'll say, improved notion. In the mid-70s.
I think I asked you this already, but that's Levin from Cook and Levin, the SAT
Yeah.
guy.
Yeah.
He was busy.
Yes. Yeah, Levin was in fact, he was a student of Kolmogorov, and he's still alive. He's a professor in Boston. Near.
Wow.
Yeah. Chaitin is also still alive. Kolmogorov passed away, and also Solomonov. I'm pretty sure. I say at first it's less intuitive. I must say once we truly get the vibe and we're used to work with prefix complexity, in the end it is intuitive. And when we go back to the plane complexity, we think, oh no, that's plenty of cheats. There are cheats in the plane complexity. Okay, I'm just claiming it now. We're going to see what are those problems once we get there, and eventually motivate prefix complexity. But for now, yeah, the section is plane complexity. And then, yeah, so with respect to the last point, I'll just say it solves many problems that were here. So, having said that, let's go to plane complexity. And the key idea yeah, well, that's the key idea. We want to produce the string x from some description that I'm going to call p. And we're going to be looking for short descriptions. Like, ideally, as short as possible. And in fact, algorithmic complexity is the length of the shortest description for a string x. So, the algorithmic complexity of a bit string x, it's a finite bit string. Just write it differently. Some redundancy here, 0, 1 star. Right? X is an element of 0, 1 star. And its algorithmic complexity is the length of its shortest description. So here I have some p in my cartoon or in my diagram. I have some p that I feed to some description method, and from p we get x. So p would be one description for x in that case. Now note that here description refers to p, but implicit I have a description method. So a shortest description, yeah, okay, but how does these description work? So I have on a fixed description method.
Like a universal Turing machine?
We will get to that exactly. Actually, my next sentence. Not universal yet, but at least, you know, if we really want to, so yeah, just to put some like names on what I call it, P can be the description and the box is the description method. What do I do with P, which is just a bit string in the end of the day, to extract X out of it? I'll have to do something to it. Now we right away get that, oh, well, if we want that to be physically possible and doable, we will want this box to be computable. So we want our description method to get from a description to a string to be a computable process or just a computation. Let's just say it this way. To be useful, there ought to be a computation and when we think of a computation, we can think of a Turing machine. And so a Turing machine that can generate X from its description. Yeah, so this box has to be some form of computation. Therefore, it has to be a Turing machine, which has a description, which we will understand as an input for the Turing machine, or a program, and which produces the output X. We'll be looking at the minimal, shortest program that can produce X. Now, yeah, we managed to speak of Turing machines without using really much the word program. We're now going to use it. Just as a another space here. Definition. An input of a Turing machine shall also be called, I cannot say that, right? I cannot say something shall be called.
Sure, why not? Yeah, it shall be called.
Yeah, I can?
Yeah.
Okay. It has a different meaning than I shall do.
Yeah, it's more, I don't know, formal sounding. It just means future tense. Like,
Yeah.
I will do it. I shall do it. It's like more fancy sounding, but yeah.
Okay. Thank you.
Or formal sounding, I guess.
Shall also be called a program.
Why the input is the program?
Yeah. If you think of the Turing machine as a special purpose computer, it's fixed, it's built. I give it a P as an input. Now, our brain is used to think of a universal computer, and it will also qualify, right? The input of a universal Turing machine shall be called a program. And then the program will be, either programming the Turing machine or programming its input, but we don't really mind. It's still a program. It's still going to be the input of a universal Turing machine. Yeah, we are not really used to think of special purposes computer, but you can define a fixed Turing machine, which is sort of semi-programmable. It's not universal, but we still want to call the input of that special purpose computer a program. In some cases. So I agree that basically it's naming. We have done Turing machines by just calling inputs of Turing machine. Now, the universal Turing machine takes as a program, as an input, two parameters. One which will be able to determine which Turing machine to simulate, and one which says basically on what input should it be simulating. Okay, on that, so we can view every Turing machine as a possible description method. It's going to be sometimes a special purpose description method. So there are as many description methods as there are Turing machines. And maybe what matters here is that if P admits a program P for which T of P equals X, then just to connect with what we've done, then P is a description for X. Under the description method given by T. We can thus define the complexity of a string x with respect to t. Okay, I know, like we might be jumping ahead and want to say, oh yeah, we're going to take a universal Turing machine. It's good, but it's at least good to know that the definition of complexity works for all t, for all Turing machines, not just for the universal computer. I'm going to have to write with respect to t. So we can define the complexity of a string x with respect to t it's really like to be understood with respect to the description method given by t, but I'm just going to be writing with respect to t as c sub t of x. And yeah, in that example, then I have p, I wrote tm, here I had a specific one, I have t. You know, t is my description method, it's my computer, perhaps a special purpose computer, perhaps any kind of computer, it's a Turing machine. And we're looking for possible descriptions, p for x. Now, not only we're looking for possible, but ct of x will be the length of the minimal one, the shortest one. It's equal to the minimum overall program of the length of the program such that t of p equals x. There are plenty of bit strings which when I feed into t, they don't give me x. I don't care about them. What I care is all those bit strings p, which when I feed into the Turing machine t, they produce x. I'm looking at the shortest one. And the complexity of the string x with respect to the description method given by t is going to be the length of that shortest one. Now this definition is incomplete. Why? I can have a problem with that.
The whole thing, I mean, it cannot also.
It can, yeah, indeed, this computation, there are some inputs for the Turing machine t, let's call them q. Or a fixed input q for which t of q doesn't halt. If it doesn't halt, then it does not equal x. But there are some Turing machines which, you know, like t is so far very general. It can be a constant Turing machine. It can be a Turing machine which always outputs number 7 or bit string 1 1. Whatever. It always outputs 1 1. So what would be the complexity with respect to that Turing machine of the string 0001? Well, there's no program that I can feed into t which would yield 0001. So it's infinity. Yeah, we just have to extend it by this way. So it's equal to that, and ct of x is equal to infinity if no p exists. P such that tp equals x exists. All right, that's a definition, by the way. And what have we defined? I'm not happy to say that we have defined the complexity of a string. We have defined the complexity of a string x with respect to some Turing machine T. Yes?
But maybe if I change the Turing machine, if I take another one, also the description can be different.
Yep.
Okay.
Indeed. Well, it so far seems a little bit annoying because we have not defined one measure of complexity. We have defined infinitely many measures of complexities. You know, I've defined a function Ct of x for any t, for all Turing machines t. That's my next sentence. It's a good sign when I naturally want to say something and it's my next sentence, because it means that it was my flow of idea when I was preparing my course. And I'm not getting into a different flow, which could happen. Note that for each Turing machine T, we have a complexity measure. By which I mean some mapping from a string x to how complex it is with respect to t, namely the length of the shortest program for t, Ct of x. Okay, so you can, you know, for fun, you can think of what would be Ct of x like if the Turing machine is this one. And you might get, oh, it's not super interesting, but it gives me something, it gives me some idea. Like, I guess a natural choice would be, imagine a Turing machine which computes the identity function. Okay, so the good news is that we will never get into this case. Because with the identity function, there's always a program which prints x. But it's x. You know, and then what would that spit? It would be, so Ct of x, when t is the identity function, it would be the length of x. All right, not bad as a complexity measure. Why not? The length of x. It's a little bit frustrating when x is 0, 0, 0, 0, 0, 0, 0 for 10 to the 10 bits, because we're like, ah. It's telling me that it's the length of x, so 10 to the 10, but intuitively it's missing all the fact that there's nothing into that string. But then there would be another Turing machine, which would be very good at recognizing when when it's only made of zeros, you know, there will be a very short program for it. So the beauty is that yes, we have infinitely many such complexity measures a priori. But the existence of the universal Turing machine, which will basically make them all collapse to one single relevant idea. I somewhat, for now, generically refer this to the following sentence. One of them is smaller than all the others. All right, I have infinitely many functions of complexity. The gist of the idea is to have the length of the shortest program. So it would be fun if one of those measures is basically, quote, smaller than all the others. It's like a minimal way of characterizing a complexity function. And just as a reminder, let ij be defined as I bar j, which, as a reminder, is 1 to the I, 0, I, j.
What's the length of I?
Oh, thanks. Yeah, thanks. I made a mistake.
Like how many,
Yeah.
the number of ones tells you how many bits I has.
Correct. Yeah. One to the length of I, 0, I, j. So when you read this, you can decipher I and j. And well, that was just a reminder because we had the universal Turing machine that we met. U be the universal Turing machine such that what was its defining property? So it was expecting an encoding of that form, U of ij, and it was simulating Turing machine I on input j. Okay, so that's a promise to which we will be back, to which we will come back, the fact that we have infinitely many complexity measures, one of them is smaller than the others, and sort of building it up by by reminding you of the universal Turing machine. Before I erase, are there any questions?
That is that ij will be our program, right?
Yeah, correct.
But why should we have to encode the length of I and not the length of j? Wouldn't that be smaller, for example? So there is a problem.
Wouldn't what be smaller?
Keep it in mind, Lorenzo.
Okay.
I think that what you name is equivalent to some of the problems we're going to be meeting with it. I think. Yes, in fact, yes.
You're just asking, why do we have to encode the length of I but not the length of j?
Maybe the length of j is smaller in some cases.
Oh, I see. Okay. Yeah, if j is smaller, then you'd be more efficient doing it the other way around. Okay, I see.
In fact, for plain complexity, I could have taken any computable bijection or any computable pairing. Yeah, this is in fact not even a bijection technically.
Right.
So far, it's just like a trick to encode a pair of strings into one string and easily decodable. There are other tricks which would be like to work on the diagonal like that, you know, to encode pairs of string into one single string. Mm-hmm. Definition. the plane algorithmic complexity Cu of x of a string x is defined as well, nothing has changed basically. We had Ct of x, now it's Cu of x equal to the minimum, min, not mim, minimum overall program of the length of the program, but yeah, not any program. Which one? A program for the universal Turing machine U to produce X. And yeah, as I said, it's nothing new. As a concept, I just applied this definition here with t equals to u. So note that for that I had to fix a specific universal Turing machine u, and so, connecting with Lorenzo, a specific way of encoding a pair of objects into a single object. There might be various ways to, computably encode a pair of objects into a single object. Pick your favorite one and define a universal Turing machine u this way, and then define Cu this way. Theorem it has various names, and I think I'm going to name them all because they all tell us something about the idea behind this theorem. In order, I think, in the pedagogical order in which we will understand what this theorem means, additive optimality of U okay, that's first name. The invariance theorem that's another name we could have called it. Or Cover and Thomas call it universality of algorithmic complexity. Universality of algorithmic complexity. That's just the names we give to the theorem. For any Turing machine, T, there exists a constant Now C is usually a good name, but I don't trust myself to be able to distinguish between capital C and lowercase c. Call it BT. The constant BT. The constant depends on the Turing machine T. By the way, it would have been implicit. Usually when you order quantifiers for any Turing machine T, there exists a constant. Well, then the constant might depend on T. And I make it explicit here. Such that Cu of x is smaller or equal than Ct of x plus that constant. But this holds for all x, for all bit strings. Okay, so it is the meaning by which it is a constant. It's not a number which depends on x. And that is what I had promised here. One of them is smaller than all the other. Right? We have a family of functions. X are bit strings, but think of them as natural numbers. There's a bunch of functions, as many functions as there are Turing machines. But Cu is one of those functions, and it's smaller than all the others, up to some additive constant. Okay, now let's prove it. So let T be a generic Turing machine, and we want to have a generic input X, but if the input x is such that this quantity is infinity, this is trivial, right? Their left-hand side is smaller than infinity. So let's start with if Ct of x is smaller than infinity. In my notes I made smaller or equal, but that's a very bad sign. It means what? It means that, well, this thing is defined so that there exists at least one program for which Tp of x, Tp equals x. And it means that the machine T can compute x by some program Q with length of Q equals what? Ct of x, yeah. I'm just expanding the definition. I said that this case is boring for all the x's such that this quantity is infinity. So let's look at when it's smaller than infinity. Ct of x is defined. It has possibly many programs to compute x, but what matters is that it has a minimal program for computing x. This program is Q. And yeah, Q is the minimal program for T to compute x. That's what it means. I think I'm gonna stop here. I'll just continue the proof here below. But reminding our favorite enumeration of Turing machines, T is equal to Ti. It has some index. For some I. Therefore, U can also compute X. Via the program P equals I comma Q, the encoding of I and Q. Okay, the Turing machine computes X with the program Q, but the Turing machine T is Ti for some I, and the universal machine U can simulate that Ti if it's given I as a first input here, and Q as a second input. So yeah, what U will do here, to be more complete, U on input IQ, well, by definition, we'll do Ti of Q, and then yeah, that's cool. It simulates machine I on input Q. It's one way to get X. But what's the length of P? The length of P is equal to, now this is where it comes interesting to have it, a recursive pairing which is not so messy because we can compute somewhat easily the length of P. It's twice the length of I plus 1 plus the length of X. No, the length of Q. Right? If we plug this in this formula, I have 1 to the length of I, 0, I, and then I have Q. So the total length of that is, well, the length of I here, the length of I here also, because I have as many ones as I have the length of I, and I have a 0, which is a delimiter. This contributes to the plus 1. And here it's not J that I have, it's Q, but that's the length of Q. Well, there you go. This is the constant. It's independent of X. It's my constant dt. It depends on the Turing machine T, but not on the X. And Q is what? Length of Q was, by definition, basically was the CT of X. So I'm going to write this first. CT of X plus dt. I'm not exactly done. What have we done here? We started from the fact that, okay, CT of X gives a number smaller than infinity. That means there's a program for T to compute X. That program is Q. And we're like, oh yeah, the universal machine is very powerful. It can simulate the computation of T. So that entails also a program for U, the program P given here. And that program has length this. Now what we have done, we have exhibited one possible program for the universal machine to compute X. But by definition, CU of X is the length of the minimal program. So what we've done is an upper bound on the minimal program. If I told you, oh, one program to compute X has length 500 bits on the universal machine, then the minimal program has length smaller than 500 bits. These arguments will come back again and again. Oh, I stopped my proof here, but I should say, I should at least write a note on what I just said. This is one program for U to produce X. Therefore, the minimal program is smaller than that. CU of X being the minimal program to compute X is smaller and equal than one given program to compute x. The length of one given program. Since, let me write a sentence, simulating t on input q is one way for you to produce x. And the minimal way for you to produce x, or the shortest way would be an ambiguous term, the shortest program for you to produce x, namely cu of x, is smaller or equal. To length of p. Okay, I will not all the time say that, but the first time it arises as an argument, it's good to understand it cleanly. We have exhibited one way for you to compute x by simulation of t on input q. Simulation of t entails that constant bt, which is independent of x, but the input will encompass x. That's the size of the input that was needed to give to t. Since we've exhibited one way for you to produce x, it means that the minimal way for you to produce x is going to be smaller than that. This is what we wanted to show. I'm over time. Let's have a break. Let's have a 15 minutes break. Reconvene after. All right. A universal Turing machine U, well, it's already universal, that has the property star, as in the star that I made over there, I wrote over there, is called additively optimal. I erased it, but it was on, I believe, that board. The Turing machine that we've seen in the course, even in the course of Turing machines, even before today, that I repeated, it's the same U, it's the U that we've used in that proof, is an additively optimal universal Turing machine. It has that property. We just proved it for that U. Many other universal Turing machines are additively optimal, but some universal Turing machines are not. Yeah, there are there is such a thing as a universal Turing machine which is not additively optimal. As I told Lorenzo, I came up with a ridiculous example, but suppose that the Turing machine, it expects two inputs. And suppose that it expects a power of 5 multiplied by a power of 7. And if it indeed receives a power of 5 multiplied by a power of 7, it will simulate the Turing machine number exponent of 5 on input exponent of 7. It is a universal Turing machine, but if we try to make it work, we will realize that it's very inefficient in the way it's encoding its input, so that we will have like large constants here, or even we could get exponential here. We will not get this property. Whereas the one that we had, it was expecting an input of the form I bar j, and the fact that it was expecting input j permitted us to have, well, this was sort of the length of j, which was the length of q in the proof, and this was the length of I bar, which is only a function of t. Yeah, so you can come up with plenty ways, your favorite way of defining a universal Turing machine, which is not really efficiently encoding its input, basically, in which case it will not be an additively optimal Turing machine. Now, what we can do, the invariance theorem. Oh, by the way, yeah, so far I sort of addressed additive optimality of U. We proved that the U that we defined is additively optimal. It's one way to understand this theorem. Now, it is usually called the invariance theorem, so let me call it this way, and we're going to justify why it's the invariance theorem. Can be applied by setting t equals v, where v is another additively optimal universal Turing machine. What would we get? Yeah, this was oh, I messed up. Sorry. This is not the star. This is just a definition of CU. Sorry. Don't hesitate to shout if you see things that are wrong. This is the definition of additively optimal. Okay, and now what are we doing? We're applying this theorem to specific case of Turing machine, namely a Turing machine V, which is also an additively optimal universal Turing machine. We would get Cu of x is smaller or equal than Cv of x plus some constant. All right, there exists Bv such that Cu of x is smaller or equal Cv of x plus the constant Bv, and this holds for all strings. But there's no preference. I could say, yeah, V will be my simulator of my machine U. Namely, they're also, I mean, V and U are completely symmetric. They have the same properties of being additively optimal universal Turing machines. So there exists BU such that I have to reverse all this. CV of x smaller or equal CU of x plus some constant BU for all x. Now you can play with those expressions and realize that this means there exists BUV such that the difference between CU of x and CV of x is smaller than a constant BUV for all x. Right? BUV is the maximum of BU and BV. So these two measures of algorithmic information, you know, they're defined for each x. They're function of x. Think of x as all strings or as all natural numbers. And they differ only by a constant all the time. They will go very large. You know, there are some strings which we call them random. We wanted to call them random last time. They don't have short programs, so they will have very long shortest programs. And if it's a very long shortest program for U, then it's also a very long shortest program for V, because these two measures are just, they only differ by a constant. And that constant, you know, depends on slight details in ways in which we define U, slight details in ways in which we define V. But really, if U and V are additively optimal, they can simulate each other with only a constant overhead in program size. So here I will do an apartheid for notation, a notation that we use quite often in algorithmic information theory, and I assume you might have seen that before. In fact, I'm pretty sure. But it will be a reminder. The big O notation. Yeah, you know that, right? Okay. Okay, so I'll go just for the quick version. G of x equals big O of f of x. They're functions on the natural number. X takes value either bit strings or natural numbers. If there exist constants, if there exist constants, what are they? Say C and x0, such that for all x greater than or equal to x0, g of x in absolute value is smaller or equal than c times f of x.
I think you should put the absolute value also for the f.
Should I?
But the sign shouldn't matter.
Yeah, if I always write a positive function here.
Well,
Then-
yes, in general it can be also negative.
Okay.
Yes.
But I will always write things of the kind order of 1, order of log x, order of
Yeah,
x
yeah.
squared. I'm going to write positive functions here, but I don't mind if we put a... What matters is that...
C, you can make C like more than 0. I know 0 like.
Yeah, well,
But like if f is like negative, for example, you just take c that is minus, has minus, and then you cancel out.
yeah.
Yeah, that makes sense.
But if we really want to make it annoying, can we choose a f which oscillates between positive values and negative values? In which case, just putting a global negative number doesn't fix that problem, but Lorenzo's solution to put absolute values does.
Yeah, usually, well, the alternative definition was that the limit of the absolute value of the ratio
Yeah, but that's small O, isn't it?
is?
That is small O.
No, small o is that is equal to 0.
Ah,
Big O
okay.
is that is equal to a constant that is not.
Yeah, okay.
With
Ah,
small
okay.
you can define it as well, like this, just remove the equal. This, if it's less, it's small o. If I'm not wrong. Right? Small o, it means that it's like upper bound, like a big O, it means like it can also be equal.
No, that would be you would need that c to tend to 0 in some sense. I don't know how to express the small o.
You
with
can just
this
remove
way.
the equal there, if I'm not wrong.
No, because you can just take an infinitely smaller c, like c minus epsilon for some epsilon, and that would be still smaller or equal. Yes, it doesn't change that much.
I'm gonna add my other sentence just to, I think that's like the analysis way of writing it. It's basically, if g of x is order of f of x, means that after a certain, it can do whatever it wants at the beginning, that doesn't matter, but after a certain threshold x0, it will be bounded by a constant times the function f of x. So typically we're going to have f of x, for example, being a log n function. And so g of x, if I say g of x is, log x, if g of x is order of log x, it means that maybe g of x is a very messy function. It can be, hard to describe, and that's the usefulness. But what matters is like, in absolute value, it's bounded by some constant time a logarithm in x. So we will typically use these arguments to say, oh yeah, we ignore this term because it's a very small term with respect to some dominating term, which is linear in x. That's usually the reason why we do it.
According to Google.
Oh, yeah, yeah, there you go. Sometimes I'm like, I would like to have Google right now. I'd be more powerful.
Google.
Yeah, what did you say?
That one is correct.
That one is correct?
Little o, it also says that you can write it as without the equal.
Okay. Okay.
It works.
Without the equal.
Like little o, you just remove the equal. It's
And
not
that's
small
it.
o, little o. No.
It surprises me.
For all constants.
Ah.
Not that there exists a constant c.
Yeah.
For any constant c more than 0, you
Yes.
have that.
Let me just go out of this
Okay.
rabbit hole because anyways we're not gonna use little o for now. And not that I think so. For those who are more intuitive, I'm gonna write my other sentence. It might be helpful. We denote
Whereas here it can be
O of f of x to be a quantity
Prendi uno costante di merda e lo fai arrivare sotto.
whose absolute value does not exceed f of x by more than a fixed multiplicative factor.
G.
No, this way of writing it is the quantity is like G. Yeah, so if I say, okay, let me just go back here, it simply means that I could say, oh no, I'm not going to do that. I'm going to use this notation to say Cu of x equals Cv of x plus O of 1. It permits me to write this. Because this equation says that, yeah, the function Cu of x and the function Cv of x, they differ by at most some fixed constant. But the actual exact difference can be very chaotic and messy, and sometimes it can be a positive quantity, sometimes it can be a negative quantity, but in absolute value it's smaller than a constant. So I'm just going to write it's O of 1, order of the function 1. It's a quantity which is bounded by a fixed multiplicative factor times the function that is inside my argument O of. Here my function is 1. So it's a quantity that is bounded by a fixed constant. Okay. We thus see that the choice of reference additively optimal universal Turing machine only matters by an additive constant. Independent of x. In most cases, we consider this to be irrelevant. As it is, irrelevant. For strings large enough. If I compare the plain complexity of the string 0, 0, 0, very small string, with respect to the universal machine U, and I compare it to the complexity of 0, 0, 0 with respect to the universal Turing machine V, it might be a large gap. It might be that U is such that it has a very, very short way of writing down 0, 0, 0. I don't know, like 1-bit program does the job. But V has only comes with larger programs, like programs of 100-bit would be the shortest one. So for short string X, maybe this matters. But eventually, once we consider a very large string x, the fact that these two measures differ only by a constant, we will consider that constant to be irrelevant. They're basically grasping the same concept. Because for strings large enough, that constant will become irrelevant.
I have a problem here because you're trying to build a complexity structure on this set of strings, but for example, in the usual complexity theory, you have that the complexity structure is built on the concept of the input size, for example.
Yeah.
Here, what's exactly like? Also in the big O notation, we use that x and x tends to infinity basically, and we have this asymptotic behavior that we only care about. But in that case, what is exactly tending to infinity?
Either x that you re-understand as a number, or we might prefer the length of x. They're obviously both related. The length of x is roughly log x. So this is what this O of 1 means. Because this is an equation for a variable x, if you want. You know, I have, for each x, I return a number, cu of x, a function. For each x, I return a number, cv of x. This O of 1 means a quantity which is bounded by a fixed constant times 1, so a fixed constant. And constant in what? Constant in x.
Right.
Thanks for the question. Yeah, we're either going to be using x or the length of x as a parameter. Most of the time, the length of x. Okay, so, you know, once we had a concept of an additively optimal universal Turing machine, and we realized that, oh yeah, okay, they really are grasping the same idea, since we're going to discard those O of 1 error terms, because we're interested in strings that are large. Then we have a notion of this is the invariance theorem, basically. It doesn't matter which, if we don't want to bother into precise details and we're willing to tolerate a O of 1 error term, then we don't mind which reference machine we have chosen. So the invariance theorem motivates us to drop the U in CU. We simply write C of x. For the plain complexity of the string x. If we simply write C of x, we understand that we're building a notion, that if we really want to have a well-determined number, it needs to be implied that we fix a reference Turing machine here, U. But since we realize that they only depend by a fixed constant, and we're going to ignore those constants, we simply drop the U. Okay, let me go here. Are there questions?
I think additively optimal is still it's still a bit fuzzy for me. Like, I think maybe because I didn't understand the example, like, it's hard for me to imagine what I mean, I understood that it's related to how your Turing machine is actually interpreting its input, but I didn't understand what a not additively optimal Turing machine.
Cool. Thank you for asking. I think I'll leave. I'll say something, but I'll leave you some work. Take the machine W, which expects a pair of input ij, and it's gonna do this. It's gonna do Ti of j. It's a good sign if we want it to be a universal Turing machine. No. It expects a program for universal Turing machine. It's going to be Ti of j, simulate the machine number I on input j if P is equal to 1 to the I, 0, 1 to the j. I'm not making a fuzzy, like I'm not encoding into prime numbers like I gave this example, and it's true that it's a bit hard then to realize what it means. But, so no, it's a Turing machine. It's going to check its input P. And if P has the structure a bunch of ones, a 0 and a bunch of ones, and then a blank, he's going to say, okay, I have a valid input. I'm going to do my job as a universal Turing machine. I'm going to count the number of ones that I had initially, and that will determine I. So I will simulate machine number I. And then that's just a delimiter. And I'm going to count the number of ones after. That gives me a parameter j. And I understand the second parameter, namely the number of ones after the 0, but before the first blank, as the input of the Turing machine Ti. Okay, it does that if P really qualifies as a string of this form. And it just prints empty string. It halts if P is not of that form, is another string. Okay, I'm basically just putting this condition because one could say, yeah, what does your machine W do if it receives an input 0, 0, 0? Oh, it's not of that form. It checks, oh, that it's not a valid encoding. Halt and produce nothing. Verify for yourself that it's a universal machine. I think that's clear from the first line. It can simulate all other machines. But play with it and try to do the theorem by using not U here, but W. And see how it will be very annoying. You will not get Ct of x plus constant. You will get a large function of Ct of x plus constant. Any other questions? You know, in some informal or like bird's eye view of algorithmic complexity, some people say, oh yeah, it's the length of the minimal program on a universal computer. Yes, but you know, it's like read the details, and in the details, it's not any universal computer. It needs to be a additively optimal universal computer to have this notion of machine invariance. And since we're doing a course on it, then I'm putting the details on. Okay, it's quite enlightening to think of the invariance theorem just a little beyond Turing machines. And in fact, it's going to be useful because, as you all know, we don't really like or even know how to actually code Turing machines. So it's a bit embarrassing. we use Turing machines as a canonical model for Turing machine to encompass the notion of computation. We could put our hands into the rules of Turing machine and actually really do code algorithms in Turing machine, but most of the time what I'll do is I'll invoke a high-level algorithm, and we know, oh yeah, by Church Turing there's also a Turing machine that does it. And so yeah, it's quite useful to think of algorithmic complexity beyond Turing machines and by invoking Church Turing. Yeah, let me just write Church Turing. And so by Church Turing, I'm sort of thinking, yes, okay, Turing machine's fine, but we've seen that there's many other models of computation. We have computers, we have programming languages for computers. What about the minimal program in Lisp for computing a string X? What about the length of that smallest program? What about the length of the smallest program in Python to compute the same string? I ask those questions. What is the length C Lisp of X of the minimal Lisp program for a string X?
It's funny because people do this for fun challenges.
Yes.
Occasional challenges where people try to write the shortest possible program in a given language to do a certain task.
Yeah, there are contests of that, no?
Yeah.
Yeah.
So you try to have like 207 characters instead of 212 or whatever.
Yeah.
There is also the unreadability code contest. Yes.
What's that, Matteo?
Unreadability code contest. You have to write unreadable code, and the one that is more unreadable wins.
Oh wow.
Yes, cool.
Like a C program.
Yeah, it's like a C program that I don't know looks like an house or something like that.
Oh, well, at least.
Same question, but what is the length C Python of X of the minimal Python program for the string X? And well, technically speaking, this theorem really leveraged the fact that the machine U was simulating the machine T, so it was really like a theorem about Turing machines. But you might see it coming that we also have an invariance notion here, namely that the Lisp programming language admits a Python interpreter. So a Python interpreter is going to take what is supposed to be a Python program, it's going to interpret it, and it's going to do exactly what a Python computer, what the Python interpreter would do on its own programming language. So they can simulate one another. And vice versa, that's what I meant, by simulate one another. In Python, there is a Lisp interpreter that will get a program that is a valid Lisp program and run it on Python. And those interpreters are fixed algorithms. They're written once and for all, and they work for all inputs.
Like a backend of a compiler.
A what?
Backend of a compiler is the same, and front end it changes.
Backend of a compiler?
Yeah. I mean, you get the code, you give it to the front end creates something called abstract syntax tree, and then it gives it to the backend of the compiler, and the compiler, like the backend creates the actual assembly or whatever.
Okay.
It sounds different though. Like you just use the front end of a language to implement a different language.
Takes one language and brings it to another one.
I wish I could have more knowledge on that, but that's really beyond me. You are my source, Pasquale and Matteo and all of you. Thank you for being here and telling me how computers work.
Excuse me, I was thinking it's difficult to explain, but maybe assume that I don't know, in Python is more easy to write a smaller code. Okay, but I think that this is related to the fact that maybe the Python interpreter is bigger.
Yes.
This is a problem for that, I think, because if I consider Python is like cheating, yeah, because Python works on a specific compiler. So
It will be cheating. It will be appears like it's cheating for the first strings. Like Mathematica, it has so many embedded functions. Just say like Fibonacci equals, and it's going to tell me its first bits. Whereas if I don't have such a elaborated built-in resources in my programming language, I'm going to have to write all the loops and the recursive programming to get to the Fibonacci. So for the first strings, it's gonna feel like, yeah, Python is superior. But I should write down the equation, and the moral of the story is that once we get first strings large enough, it doesn't matter anymore.
It's a constant factor.
It's a constant term, yeah.
It's like, I don't know, 5 lines more of code compared to the other one.
Yeah, you just append with the interpreter. What I call the interpreter, but you seem to say it's a
No,
compiler.
interpreter means that like, you get some code and you just execute it, right?
Yeah,
not exactly.
Yeah, okay, not exactly, but like...
okay. There is a universal constant which I'll call B Lisp semicolon Python, such that C Lisp of X minus C Python of X in absolute value is smaller than that constant. And similarly, it's actually quite similar to what happens here. Like U can simulate V and V can simulate U with constant overheads, and you can define this constant to be the maximum of the two. You know, Lisp can simulate Python with a Python interpreter. Python can simulate Lisp with the Lisp interpreter. So if you give me one recipe to produce X on Python, then I can use it and interpret it on a Lisp to give basically a simulation of Python via the interpreter and then the Lisp program. So for, yeah, that's a constant. It might be a large constant. So for many strings, it might create a large discrepancy in the shortest program for string X on Lisp and the shortest program for string X on Python. What this tells us is that eventually, when the strings are going to be large enough, these measures are going to grow beyond constant, and they're always going to follow each other. And so eventually that constant will become irrelevant. I'm over time. I think on Thursdays we're fine. We're not rushed, so I'm happy to stay if there are questions.